Welcome to Lecture 31B. Here basically we're going to apply the divergence and Stokes theorems, that is the 2D or 3D representation, under problematic conditions which I'll define shortly. So the material for this lecture comes from Reading Assignment 4, Section 4.7, and the objectives are to show how the divergence theorem, Stokes theorem, and Green's theorems, which are essentially the 2D analogs of the divergence and Stokes theorem, can be used for irregular regions or when the field is undefined at one or more points in the region or on a closed surface or closed contour bounding a region. So the concepts and visualization skills we'll be dealing with here are introducing cuts to create regions which are enclosed and adding contours or surfaces that avoid points at which the field is undefined. All right, as usual, the second slide is just a summary of the content to follow, and so you can quickly scan through it, and we'll move on to the next slide. Okay, so we're going to apply the divergence and Stokes theorem if a region is not simply connected or simply enclosed, or the regions contain problematic points. We'll get into what these things represent shortly, but I just put everything there in terms of very sort of short summary statements. Now, up to this point, when we applied the divergence theorem, Stokes theorem, or Green's theorems, we basically made some assumptions regarding the nature of the fields and the surfaces or regions or contours that we're dealing with. And so I've just basically written down the various cases basically that we'd be interested in making sure are in fact valid. So first of all, the partial derivatives of the vector components are continuous within the domain for a divergence theorem and on the surface for Stokes theorem's problems. Surface, of course, doesn't have to be flat, it can be curved. The vector valued functions are continuous on the closed surface for the divergence theorem and on the closed contour for Stokes theorem. And third, a closed contour must completely enclose an open surface for Stokes theorem, and a closed surface must completely enclose a domain for the divergence theorem. Note that a domain in 3D is a volume and a domain in 2D is a planar area. So I just make this as a statement because I'm not going to repeat this. I just say either region or domain, and it's implied whether or not we're dealing with a 3D problem or a 2D problem. So the general question is as follows. Can we still use the divergence theorem, 3D, Green's flux theorem, 2D, Stokes theorem, 3D, and Green's circulation theorem, 2D, if one or more of the conditions stated above are not valid? And the answer is yes, but we'll have to find ways of circumventing the problem so that the new problem basically is one in which all the conditions above are satisfied. So first of all, let's look at classification of contours and classifications of regions, starting with basically 2D and then moving to 3D problems. So for contours in 2D, we have basically terminology that's being used. And so we characterize contours as being simple versus not simple and closed versus not closed. And now if you take all possible combinations of these two, there are 4 in total. And so I've put a little table on the side here. Simple, not simple, simple, not simple, closed, closed, not closed, not closed. And then a simple diagram to illustrate these 4 conditions. So this would be considered a closed, simple contour. And this is a problem that we've been using all along. So there are no problems with this one. Closed, not simple. All right, so this one is potentially problematic because you have a crossover point here. And so you have to sort of keep track of what's going on. There's a region here and it's a region here. So in principle, this is a problem that could be solved, but you've got to keep your eyes on this one. Not closed and simple, not closed, not simple. Clearly, we're not going to be able to use, for instance, Green's circulation theorem or flux theorem here because it's required to have a closed contour. But nevertheless, this is just showing you ways of characterizing contours. So again, I just mentioned that a curve which is simple does not have any crossover points. Notice there's a crossover point, so this is not a simple curve. And also closed curves enclose regions. So for instance, this encloses this planar region that you see here. All right, now let's classify regions. Okay, so there are basically two things that are used to characterize regions. One is whether or not the region is connected versus not connected, and is it simply connected versus not simply connected. Again, there are four possible scenarios, which I basically have outlined here in the table. So let's look at each one of these in turn. So for instance, this type of region would be considered connected and simply connected. And these are the regions that we've been looking at in problems so far. This would be considered not connected and simply connected. And so these are like two islands, but each region separated from each other could be treated quite nicely. Here, on the other hand, we have something which is connected, but not simply connected. And what does that mean? If you, for instance, take any contour within a region and you try and shrink it to zero, in other words, smaller and smaller, if this contour, when you keep shrinking, remains in the region, then there are no issues. But the moment that you find that you have to basically go outside of a region in order to shrink this contour to zero, then basically we have a not simply connected problem, and that is problematic in terms of applying either Green's flux theorem or Green's circulation theorem. So this is a real problem that needs to be solved. Here we have not connected and not simply connected. So here, for instance, this is the same as this one, and you have two different regions. So in principle, we could solve this type of problem, but the headache is to deal with this, and that's basically what we're going to be outlining. So in general, connected region just means no islands. And simply connected region implies every closed simple curve does not overlap, can be shrunken down to a single point without exiting a region, i.e. no holes. All right, so for instance, there's a hole. All right, so now let's look then at not simply connected 2D region, and we want to figure out how do we basically make this amenable to the use of Green's circulation theorem or Green's flux theorem. So this, as I said, is a connected but not simply connected 2D region. So what we've drawn here are contour 1 for the outside and contour 2 for the inside. These are just directions I've chosen to be both counterclockwise. So how are we going to basically create a contour that encloses the region shaded in gray? It's very simple. What you do is you introduce a cut. You cut this basically right down the middle here. And what you do is you have these two lines that you see here infinitely close to each other. They more or less overlap. But here we're just showing, for sake of argument, that they're very close to each other. So if you look at this now, this basically represents 4 different segments. When taken in total, enclose the region, which is the area shaded in gray. So we have, for instance, here C3, C1, C4, followed by C2. Now, since we chose C2 to be counterclockwise, minus C2 means clockwise. So this is clockwise. C4 and C3 are new, so we've just given them a specific direction. So this more or less solves the problem in terms of having a contour which encloses the region. And so now basically you want to figure out what does Green's circulation theorem and Green's flux theorem look like when we introduce this cut. So that means that a closed contour here will have 4 contributions. As shown here, this is for Green's circulation theorem. So the contribution of C1, C4, minus C2, and C3. Again, minus C2 just means you're moving in a clockwise direction versus counterclockwise direction. All right, but if you look at these two, one going this way and one going this way, they're going in opposite directions, but each makes a contribution to the closed contour integral, which means this term and this term, when added together, right here, sorry, the term here, C4 and C3, when added together, this is opposite sign to this, so when summed, gives you 0 contribution, and as a result, you end up with C1 minus C2. Now, you can also basically change this around. So, for instance, minus C2 is clockwise. If you were to have made this counterclockwise, then you could do it, but that would introduce a minus sign here. So, effectively, we can write it this way, or we can write it this way, but this depends on how we decide to label our contours. And if we do that, then it does enclose the region, and so the right-hand side, basically, of the circulation theorem does not change. It's only the left-hand side that changes. For the Green's flux theorem, it's identical. Instead of dealing with TDS, we're dealing with the normal NDS. So effectively, you end up with a similar sort of relationship. So here we had C1 and a minus C2. We have a C1 and a minus C2 here. And this now is the flux, whereas here this was circulation. Again, A represents a gray, shaded gray planar area in the XY plane. All right, how do we address a problematic 2D region? So for instance, you might have 2 points here where the field doesn't exist, right? No limit. And so we cannot integrate over a region. And so the simplest thing to do is avoid it. So what we've done is put 2 closed contours, right? One closed contour here around this point and one around this point. So we've encircled it. But that's still not enough, because if we're going to apply the green circulation theorem, we need to basically have a closed contour that encircles the region. And so the simplest way to make that happen is to introduce a cut that goes right across. And so what you end up with is 2 separate regions or subregions. And each subregion, we can basically have a contour that encloses that subregion. So here's one subregion, this gray area, and here's the second subregion. And I basically distinguish this to be the bottom subregion and A, the top subregion, right? So the cut allows us to do it. And so if we're interested in the problem as a whole, we could apply either the Green circulation theorem or Green's flux theorem for this one and this one, add the results together, and we would end up basically with a formulation of either of the Green's theorems, which now basically is valid because we have avoided the points in the region which were problematic. Note, this is similar to what you would have done in MAT290 for Cauchy's integral formula, where the poles are enclosed by contours to help you solve the integrals. So just make reference to this figure in the next couple of slides. You can flip back and forth if you want. There's not enough space, so I just didn't repeat the figures. All right, so now let's consider how we deal with the problematic 2D region when we're applying Green circulation theorem. So we have 2 different contours from the previous slide. We have the contour CA, closed contour CA, but it's comprised of 6 individual segments, shown here, C1A through C6A. And you'll notice here the minus sign, which means that the orientation of the contour with respect to the sort of convention which we had chosen to be in a counterclockwise direction is opposite. And so that's indicated by putting a minus sign here in terms of going in the opposite direction. All right, so this would be the closed contour integral for the second contour, which is CB. But again, it involves 6 individual segments. Again, the minus indicates in the opposite direction. Next step is to add these 2 equations. And by adding the equation, that means the yellow and green, making use of the fact that TS4A and TS4B are line segments that lie one on top of each other. However, one is in the opposite direction of the other, and so basically you'll get cancellation of these terms. That also applies for TS5A and TS5B, and TS6A and TS6B. So taking that into account when adding, and these cancellation of these terms ends up giving you a final solution that involves a closed contour of C1, closed contour of C2, and a closed contour of C3. Of course, this is in the opposite direction, and this one as well, with regards to the conventional sense. However, we can make them all look the same by essentially reversing the sign here and bringing a minus sign outside, as was done here. All right, so that means the contour integral has been taken care of. And on the right-hand side, we're basically just taking the 2 areas and putting them together through a union. And so we can apply basically the right-hand side of Green circulation theorem, which would be just to compute the partial g with respect to x minus partial with respect to y, and integrate over the region, which is the area that's being shaded gray in the xy plane on the previous slide. Now we can take this concept, extend it to the 3D case by invoking Stokes' theorem. And the only difference in this case that we'll be dealing with areas that are curved surfaces, and we'll be dealing with contours which are not on a plane but would be lying on a curved surface. So essentially can be easily extended. All right, so let's actually consider the case of 3D. and a problematic surface. And in this case, we're talking about applying Stokes' theorem. So this is basically the surface that we're dealing with. This could be a planar surface, it could be a curved or distorted, deformed surface in a 3D setting, but simpler to just represent it just as a flat surface here. You'll notice that the region S, which is the shaded region, right, is not enclosed by a continuous closed contour. I've noted here, for instance, that we could create a contour on the inner face and a contour on the outer face, and I've shown them with specific directions, in both cases being counterclockwise. But since this contour and these are independent of each other, this does not represent a contour that encloses the surface. However, there is a simple way of getting around this problem, and that is by introducing a cut as shown here. So by creating a cut, we can essentially create a closed contour, which is this one, that basically encloses the region. And then we let these two contour segments basically sit one on top of each other, which produces cancellation, right? In that case, this contour that we see here does enclose the region which is shown in gray. Now notice that this would represent a contour direction, a traversal in a counterclockwise direction. So keep that in mind, because that means that the area vector, again according to the right-hand rule, for this case, right fingers would point in this direction, and the thumb would be pointing out of the blackboard or out of the page, which would be the direction of the differential surface area vector enclosed by the contour. All right, the other thing is some nomenclature. Minus C2 implies that the contour C2 is traversed in a clockwise direction. So C2 is counterclockwise. Here, this is minus C2 to indicate that it's counterclockwise. All right, so the vector field would take on this particular type of form. And if we apply Stokes' theorem on the left-hand side, which is essentially the closed contour integral, then we have 4 contour segments. These are the 4 contour segments. This, of course, indicating that it's a clockwise traversal rather than counterclockwise. But because this and this are in the opposite direction on top of each other, means that these two basically, when summed, cancel. And so we're just left with the contour representing C1 and the contour C2. So that's basically what you see here. However, if we want to keep to this convention, then we can essentially say that integral of closed contour of minus C2 is equivalent to minus the closed contour C2. So this yellow then represents what we see on the left-hand side here. But this, by Stokes' theorem, right-hand side, would mean that this would be an integral of the curl of F dot product with the differential surface area vector, which is pointing out of the page according to the right-hand rule. So this is a way of dealing with the problematic surface. All right, we can also now apply Green's flux theorem for the 2D case. The only difference now being that these expressions which involve the normal component rather than the tangential component to the contour segment. So more or less everything looks the same, right? For both contours, CA and CB. Difference being now there are N's in here rather than T's. Here we will find that for the particular segments 4A and 4B, the normals are basically in the opposite direction. These segments basically are on top of each other. And similarly, S5A is normal to is the negative of the normal of S5B, and the normal S6A is opposite direction to that of S6B. And so when we add these two together, we'll get cancellation of those terms, leaving you with a final expression that looks like this, similar to the one we saw for the circulation theorem, minus C2 minus C3. But we can basically reverse the direction by putting a minus sign in front, in which case this just becomes C2 with a minus, C3 with a minus, and we end up with this expression. Now the right-hand side of Green's flux theorem basically would involve the partial derivative of x plus partial derivative of g with respect to y, which is just the divergence of the field in 2D, and the area would be the area contained between the two regions defined by the contours. Okay, and again, the area is just the xy plane 2 slides back. All right, just a note, direction of NS is to your right. It points outward when traversing a closed contour in a counterclockwise direction. And the second is that the closed contour integral taken the clockwise direction minus CW, right? This is essentially what I alluded to, that anytime you see something of this form, it can be replaced by this. Similarly, if this were a tangent vector instead, it'd have the same form as well. All right, how do we extend the concept of connected and simply connected and problematic regions to 3D, which means applying the divergence theorem and Stokes' theorem? So I've just repeated the figures here, and then I'm just going to sort of make a sort of an assertion that in 3D, we basically are just talking about the geometries being different, but the concepts being more or less the same. So a contour in 3D, that means a contour lies on a curved surface in 3D. So if we're going to invoke Stokes' theorem, then we're dealing with contours. A region in 3D. Region represents a volume which is enclosed by one or more surfaces. All right, so this would be if we're invoking divergence theorem. All right, so up here, for instance, you could say that the curves shown above become closed surfaces. So if I were, for instance, to take a trace of a 3D object, then what would I be seeing? I'd be just seeing a contour, but that contour actually lies on the surface. So it's a simple way of visualizing things. And so let's look down here. We have an example of a trace of some domain. And let's say I had problematic points right within the domain, and there. So we mentioned from the 2D case that we have to basically remove these points. So the simplest thing is to draw a contour around this point and a contour around this point. But this is a trace. So a contour in a trace format would represent basically a hollowed out sphere or closed object with a closed surface, which excludes the point that's problematic. So if we had two problematic points, you'd have these two hollow spheres embedded within the object, and then you have the external sphere. So everything that's shaded here in the sort of a yellowish color is considered to be the region. Right, so just a summary then, problematic points, black and red to your right, lie in the domain or volume bounded by the three surfaces. The orientation of the bounding surfaces is shown outwards from each surface boundary in this picture. And if you want to look at this in more detail, you can look at this here, this URL. So more or less, this is sort of the picture we're looking at when we extend things to 3D. All right, so let's look at not simply enclosed 3D region. And so this is a trace. So if this is a simple sphere and hollowed out sphere, then there would be the inner surface of this hollowed out sphere. And let's take that to be direction S2. That's the differential surface area vector. And this is the differential surface area on the outside. So how do we deal with this type of problem when it's not simply enclosed? Well, the simplest thing to do is to introduce a cut. Just cut through it. It's almost like taking a peach and opening it out. And so this is the picture you would see. This is actually a perspective diagram, and this is to be a trace of the same region. And so we create two separate halves. And of course, we put them back together again, but this is simply to visualize things. So now that we've cut them in half, then we have this region for part B, which is closed, basically enclosed by surface. How many surfaces? Where there's this hemispherical surface, there's this flat planar surface, and this inside hemispherical surface. Similarly for the top half, we have this bottom planar surface, we have this interior surface, and this exterior surface. And the arrow vectors already have been indicated here in terms of direction. So if this is taken to be outwards, then minus S2A is referring to it being inwards. And here basically this one's pointing in this direction, which is by convention correct. And this is pointing in this direction, which by convention is correct. So as far as convention is concerned, the arrows I've shown here are correct for applying the divergence theorem for the upper hemisphere, hollowed out, and also for the hollowed out lower hemisphere. All right, so what we do is we apply the divergence theorem, therefore, to each sub-region after introducing the cut. And so for the top, this is the divergence theorem for the top part, and this is the divergence theorem for the bottom part. Now we add these two equations together, and you realize that D3A is equal to minus D3B. So when you add the two together, this surface and this surface, when added, basically the flux contribution cancels. And so finally we're left with the expression shown here, that the closed surface integral, which is when you join the two together, is just going to be a contribution from S1, which is the exterior surface, contribution to the interior surface, but here at minus S2, which is pointing inwards, not outwards. Or alternatively, you want to reverse the direction so that it's pointing in the opposite direction. You can make this S2, but in that case, a minus sign goes here. When you glue these two volumes together, this is the total volume of interest, which is enclosed. So this is how you would apply the divergence theorem if you have basically a hollowed out region. And lastly, what about problematic points in a 3D region? Here I've shown just traces. And so, for instance, you have a point here, which you basically want to avoid, and a point here, which you want to avoid. And so we basically have drawn circles around them. So in actual reality, in a 3D diagram, this would be basically a hollowed out sphere and a hollowed out sphere, which encircles these points. And so in this case, if you want to apply the divergence theorem, the simplest thing is to introduce a cut like we did before. And so now you have the region above and the region below. And you can apply the divergence theorem to this problem and the divergence theorem to this problem. Then add the two results together, and you end up basically with the expression that's shown here, which is exactly the same as what we did on the previous slide. So there are ways of dealing with problems, you know, if you need to apply the divergence theorem. And so the notion of introducing cuts is a very simple technique which is used frequently. Anyway, so that more or less summarizes Lecture 31B. Thank you for listening.